Welcome to AI Frontiers. Today we explore a robotics revolution unfolding through 16 groundbreaking papers published on June 3, 2025. Picture robots that navigate hospital corridors while understanding patient needs, or machines that literally follow scent trails to detect gas leaks. These aren't science fiction concepts, they're real breakthroughs reshaping how machines perceive, think, and move through our world. We're witnessing robotics at a critical inflection point. This collection captures the convergence of neuroscience and artificial intelligence, where classical engineering meets modern machine learning. These papers represent fundamental shifts from pre-programmed task execution to adaptive intelligence. Robots are evolving beyond mere automation. They're developing genuine understanding and environmental adaptation capabilities that mirror biological intelligence systems. Computer Science Robotics, designated as CS.RO in academic circles, focuses on computational intelligence that enables machines to perceive, reason, and act in complex environments. This field bridges digital algorithms with physical reality, powering everything from autonomous vehicles to surgical robots. Success isn't measured by computational efficiency alone, but by real-world performance in unpredictable situations requiring interdisciplinary collaboration across computer vision, machine learning, control theory, and neuroscience. The first major theme involves bio-inspired navigation and spatial intelligence. The Eden framework exemplifies this approach by mimicking mammalian entorhinal hippocampal systems through grid cell representations. This isn't mere biomimicry, it's understanding why biological systems demonstrate remarkable resilience and adaptability. Consider how mice navigate complex mazes after few trials, or how migratory birds achieve pinpoint accuracy across thousands of miles. These capabilities emerge from neural architectures optimized through millions of years of evolution, achieving success rates exceeding 94% even in complex occluded environments. Medical and assistive robotics applications constitute the second prominent theme. Multiple papers address healthcare delivery enhancement and quality of life improvements. From pneumatically driven biopsy catheters navigating tortuous human pathways to comprehensive assistive systems for visually impaired individuals, researchers develop increasingly sophisticated medical solutions. These systems must meet exceptionally high standards, surgical robots cannot have off days, and assistive devices must work consistently for users depending on them for independence and daily functioning. Advanced planning and control under uncertainty represents the third major theme. Real-world robotics invariably involves incomplete information, unpredictable environments, and complex constraints. The UniConFlow system demonstrates unified constraint handling, simultaneously satisfying equality and inequality constraints, collision avoidance, and dynamic consistency without requiring retraining. This addresses fundamental challenges like navigating busy intersections where pedestrians might suddenly appear, traffic lights malfunction, and other vehicles don't follow rules perfectly. These hybrid systems combine traditional optimization with modern machine learning for computational efficiency. Multi-robot coordination emerges as the fourth theme, alongside advanced sensing technologies. As systems become more capable and affordable, applications increasingly involve robot teams working toward common goals. Warehouse scenarios require dozens of robots coordinating movements while avoiding collisions and efficiently fulfilling orders. Meanwhile, sensing advances include tactile systems requiring 99.44% fewer training samples, and remarkably, olfactory navigation capabilities enabling robots to follow scent trails for environmental monitoring. High-speed agile locomotion achievements reach 4 meters per second on complex terrain. Several breakthrough results demonstrate transformative potential across robotics applications. Bio-inspired navigation systems achieve over 94% success rates in complex environments. Unified constraint handling frameworks eliminate retraining requirements while managing multiple constraint types simultaneously. Subjective logic successfully handles contradictory sensor information in autonomous driving scenarios. Tactile learning approaches show dramatic data efficiency improvements. Perhaps most significantly, large language model integration enables robots to interpret ambiguous human instructions like, "clean up the kitchen," by generating multiple hypotheses and maintaining probabilistic beliefs over possible interpretations. The methodological approaches reveal sophisticated techniques advancing the field. Deep reinforcement learning dominates complex decision-making tasks, particularly using proximal policy optimization for high-dimensional state spaces. Flow matching and diffusion models generate diverse, multimodal solutions for trajectory planning while incorporating various constraints. Hierarchical optimization decomposes complex problems into manageable subproblems. Probabilistic frameworks explicitly model and reason about uncertainty through Bayesian filtering and variational inference. Bio-inspired computational models draw from neuroscience and cognitive science, often exhibiting remarkable robustness compared to purely engineered solutions. The Eden framework by Walczak and colleagues represents a revolutionary navigation approach bridging neuroscience and robotics. By implementing computational models of mammalian spatial cognition, Eden addresses fundamental limitations in current robotic navigation systems. The core innovation integrates grid cell representations inspired by the mammalian entorhinal cortex with modern reinforcement learning techniques. Grid cells create nature's GPS system, incredibly robust coordinate systems that don't require satellites. The system transforms egocentric motion data into periodic spatial codes, producing low-dimensional, interpretable embeddings that capture positional information in biologically plausible ways, achieving 99% success in simple scenarios. Yang and colleagues tackled constrained motion planning with their UniConFlow framework, providing unified approaches for handling equality constraints, inequality constraints, collision avoidance, and dynamic consistency requirements simultaneously. Traditional approaches handle different constraint types separately, often producing suboptimal or infeasible solutions. The fundamental innovation integrates flow matching models with constraint satisfaction mechanisms through novel prescribed time zeroing functions and quadratic programming formulations. This enables adaptive behavior adjustment based on task requirements while ensuring guidance inputs respect all specified constraints, including obstacle avoidance, admissible action ranges, and kinodynamic consistency across multiple challenging scenarios. Tang and colleagues address complex task planning challenges with their Tru-POMDP framework, integrating large language models with principled probabilistic planning for home service robots. Their work targets scenarios involving ambiguous instructions, unknown object locations, and open vocabulary object types. The core innovation combines structured belief generation using language models with rigorous partially observable Markov decision process planning. The hierarchical tree of hypotheses systematically queries language models to construct high-quality particle beliefs over possible world states and human goals. This enables Bayesian belief tracking over language model-generated hypotheses while finding optimal action sequences through efficient belief space planning algorithms. Future directions in robotics research point towards several emerging opportunities and challenges. Integration of multiple bio-inspired sensing modalities promises more comprehensive environmental understanding. Scalable multi-robot systems must handle increasingly complex environments with distributed decision-making capabilities. Real-time adaptation to dynamic human-robot interactions requires sophisticated social intelligence frameworks. Ethical frameworks for autonomous decision-making become critical as robots gain more independence. Energy-efficient computation remains essential for mobile robotics applications. These directions suggest robotics will continue evolving toward more intelligent, adaptable, and socially aware systems that seamlessly integrate into human environments. This comprehensive analysis was created through AI-assisted research synthesis, combining multiple advanced language models for content generation and organization. The synthesis utilized GPT and Claude Sonnet models for technical content analysis, with TTS synthesis powered by Google text-to-speech technology. Image generation capabilities were provided through Grok AI systems. Human expert review was conducted to ensure technical accuracy and completeness. While every effort was made to maintain precision, potential oversights are acknowledged, with full references provided for independent verification of all claims and technical details presented throughout this analysis. Thank you for joining us on AI Frontiers as we explored these revolutionary robotics breakthroughs. From bio-inspired navigation systems to unified constraint handling and intelligent task planning, These advances represent fundamental shifts in robotic intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.